Hello, everyone, and welcome to today's webinar. My name is Chris Niva, Marketing Operations Coordinator at Thermoanalytics and host of today's webinar. Our presenter today is Lauren Tetzloff. Lauren is a thermal and CFD engineer at Thermoanalytics who works closely with our customers to provide support throughout their projects and by providing technical support. She specializes in cabin and underbody simulations. And Lauren has been with the team since 2016, when she began as an intern while obtaining her bachelor's degree in mechanical engineering from Michigan Technological University. And throughout today's presentation, you may submit questions in the questions box, which we will review at the end. And we are also recording this webinar. If you're ready, you may begin.
All right, thank you, Chris. Good morning, everyone, or good afternoon, depending on where you're calling in from, and thank you for joining today. The topic of today's webinar is the effect of human position on comfort and sensation in cabins. So throughout this webinar, we're going to be focusing on a few different questions that we're trying to answer with the demonstration shown today. So the first is, does human position matter for sensation and comfort in HVAC design? HVAC design is a complex topic that must consider many different variables. HVAC energy use has become more critical for electrified vehicles while still meeting occupant comfort targets. And so together, both optimal comfort and energy savings are key design outcomes for electrified vehicles. So once we answer that first question, we'll have this second question that comes up of, when designing HVAC systems, should human position be considered as a variable? So we'll look at a demonstration model in order to investigate this. The tools that we'll be using in that demonstration model are shown here. So the first being TAITherm, which is our main thermal solver. We'll also be using the human thermal extension, which models the human physiology aspect. And then finally, we're using RapidFlow in order to model convection. And we'll just look at a few details of these different extensions. So first is the human thermal extension. This works together with the TAITherm thermal solver. The TAITherm thermal solver is what's solving our convection, conduction, and radiation, as well as environmental loading. When that is running, that runs alongside the physiology model. The physiology model is what's modeling all of the different heat rates that make a human alive and a human. So those are things like metabolic heating, shivering and sweating, and blood flow. So as we run our simulation, again, those are running hand in hand, and then those give us some various outputs. The outputs are shown from the arrows to the right. So those give human outputs such as TEQ, MRT, PPD, and PMV, and also Berkeley thermal sensation. Berkeley thermal sensation can then be used to calculate Berkeley thermal comfort. And everything in the light blue box color, that's everything that makes up the human thermal extension. And then for the convection piece, we are using RapidFlow. RapidFlow is a 3D flow solver designed for heat transfer problems. It gives fast, high fidelity results with a flexible level of detail. It also works on any complex geometry. It's easy to use, offering minimal time investment for setup and configuration, as well as automated volume meshing. And when using TAITherm and Musis, it's tightly integrated with those software packages, allowing you to have automated thermal fluid coupling and a single software solution. And the images on this slide are just showing a few different examples of the two different types of scenarios that you can set up with RapidFlow. So you can either do an enclosed volume, which is what the top image is showing, or you can also do flow around an object. So in the bottom, we're seeing flow around a vehicle, but you could do flow around a building or something like that. So now that we've introduced kind of our setup, or excuse me, our main questions that we'll be looking at, and also the tools that we'll be using, next we want to look at the specific model scenario that we'll be using for today's demonstration. For this demonstration, we are going to be focusing on a cabin cool down. But in order to get the human results correct, we also need to use some initialization models for the human. So if we start at the left-hand side of our timetable here, we can see that we're starting with an hour simulation, which is modeling a human sitting in an office type environment. The human will then do a 5-minute simulation where they walk in the ambient environment, and we can see that the solar loading is also applied during this simulation. And then finally, we have our simulation of interest on the right, which is our cabin cool down. This is going to be a 15-minute simulation where the human is then sitting in this cabin, the cabin starting from a hot condition, and then we're going to be cooling that down. Now we need these initialization human models in order to get all of our skin temperatures and the change in skin temperatures accurate, and that's important when we are looking at sensation and comfort type outputs. Just a few more details about the model. For the cabin itself, we're just using some typical material properties. The image shown here is colored by different materials. So you can see that, for instance, the windows are a different material than the body, which are a different material than the tires. For the human in the seat, we are using thermal links. This is a concept in our software that allows us to create conduction links between two pieces of geometry that are not connected. And so that's what's allowing us to create that conduction between the human and the seat itself. For weather, we are using a very hot condition since we're targeting a hot environment and a cool down scenario. So this weather is from Phoenix, Arizona, with air temperatures of around 34 degrees Celsius and a high solar load around 950 watts per meter squared. For the human itself, we're using a 50th percentile male with varying poses that we'll look at in the next couple of slides. For activity level, in the cabin portion, we're using 1, which is just for quietly sitting. And then the human is clothed with pants and a short sleeve shirt and also some shoes. The image here again is colored by material, so we can see that the gray portions are the unclothed portions of the human, and then the other colors represent the different clothing that is applied to those body segments. For convection, again, we're using RapidFlow. We're using a velocity inlet at the 2 different locations in the image. So those 2 orange boxes represent where the velocity inlets are in this model. And then we can see the curves that are applied to them. So for velocity, we have an increasing velocity starting lower and then ramping to a higher value, and then temperature decreases. So it starts out a bit warmer, kind of representing that it takes a little bit of time for the HVAC system to be able to provide a full cooling, and then decreases over time. And then since the main objective of the demonstration is to see if different positions affect sensation and comfort, we'll be using these 3 different poses. And we'll be using this terminology when we look at the results. So on the left-hand side, this is a standard grip. The hands are, about a midpoint at the steering wheel position. We then have a one-hand grip where the left hand is positioned high on the steering wheel, and then a low grip where both hands are at a low position on the steering wheel. Now that we have introduced the scenario that we're going to be modeling, we are almost ready to take a look at results. The last thing that we just want to kind of introduce here, if people aren't familiar, or just as a good refresher before we start looking at thermal sensation and comfort results, is just to go over some definitions. So sensation is how hot or how cold something is perceived to feel. We can see the scale here. This goes from very cold to very hot, and then various degrees in between there. And then comfort is whether the sensation makes the person feel good or bad. And that goes from very uncomfortable to very comfortable. With sensation and comfort, it's important to remember that a certain sensation doesn't necessarily, correspond to one specific comfort. So let's say that someone feels warm. If they just walked in from a cold outside environment into a warm room, that might feel comfortable. They have this relief from a cold environment, so that warm is going to feel comfortable. Now, let's think again, maybe someone is just standing outside on a warm summer day. Over time, that warm sensation, that might actually feel uncomfortable. So, what the sensation is and then what the comfort is, it's not always, one sensation matches one comfort. All right, so now that we've gone over that, let's look at some results from this demonstration. So first we want to look at overall sensation and overall comfort for the different poses. So if we first look at overall sensation, we can see that all three of them start out at a very warm or hot feeling, and then it decreases over the simulation, which is what we would expect since we are hoping that this is a cool down scenario. So we start warm and then we start to feel neutral or slightly cool. Now, one thing that we do see here is that we are seeing a difference depending on the different poses. So with the one hand grip, that's remaining quite elevated, still feeling warm at the end of the 15 minutes overall. Standard grip is coming down to about neutral, and low grip is even dipping down into slightly cool overall. So then if we look at the overall comfort, we can see that all of them start very uncomfortable. And, from looking at overall sensation, we can see that's because they're feeling very hot. So very hot, very uncomfortable. But then over the simulation, each one of them, is increasing and starting to feel more comfortable. And we also see differences here. So what we're kind of looking for is that, time when they're getting into a just uncomfortable, kind of a just comfortable, so that's in that -1 to 0 range. With the standard grip, we see that change occurring about 3 minutes faster than we do for the low grip. And then again, the low grip occurs about 2 minutes before the one hand grip. So we are seeing, quite noticeable differences when looking at these overall results for the different poses in that same scenario. So now that we've kind of answered the, yes, we are seeing some differences in the sensation and the comfort based on those poses, I'll look into a little bit of the why, what's driving these differences in the overall sensation and comfort. So the first thing we want to look at are some velocity streamlines. So the way these results are shown here, the first row are from 0 minutes, so just at the very beginning of the transient cooldown, and then the second row is from 10 minutes into the transient cooldown. We can just see a difference in magnitude of those velocity streamlines at the different points. And then the columns that we have are for the different poses. So we have the standard grip, one hand grip, and low grip. If we look kind of at the bottom row and focus in on that left arm, left hand, we can see some major differences in the streamlines. So if we start out with the standard grip, we can see that the left hand and the left lower arm are directly in that blast coming out of the vent. So we can see the high velocity all around the hand, all around the arm in the standard grip. With the one hand grip, since the hand is positioned higher on the steering wheel, it's not in that blast from the HVAC. So we can see those high velocity streamlines are not touching the hand and they're not sweeping over that lower arm. We are getting it a bit on the upper arm. And then we can see that some of them kind of sweep down toward the lower abdomen of the human. And then finally with the low grip, again, since the hands are out of that blast, we see that, that left hand and the left arm are a bit under the blast air. However, since the hand is out of the way and the arm is not blocking that air, we can really see those higher magnitude velocity streamlines sweeping up toward the chest and the face of the person. So depending on where that arm is in relation to the air coming out of the vent, we are seeing some pretty major differences in the streamlines. So once we look at the kind of the flow side of things, we can also look at the boundary conditions on the thermal side of things. So here we're showing the fluid temperatures and the H coefficients in the TAITherm model that result from those flow results. And we can see some similar things. So with the standard grip, we can see in the fluid temperatures that over time we are seeing some lower fluid temperatures on that left arm. We can definitely see it on that right arm that's really in that blast zone. The one hand grip, on the right hand, we can see that since it's down, we're not seeing those lower fluid temperatures on the hand and the lower arm, but we do see it a bit on the upper arm. And then if we look at the low grip, again, looking at the fluid temperatures, you can really see those cooler fluid temperatures on the chest and on the face that you're not seeing with those other positions. So just kind of a different way to look at this, looking from the flow fluid streams and then seeing how that changes the boundary conditions on the thermal model side of things. So we've been talking a lot about the hands and the lower arms. So let's take a look at some of the local results for those particular body parts. So here we're showing the left and right hand, both sensation and comfort. And we can see some differences. So again, with sensation, they're both starting out, very hot, 3s and 4s, and then they do all decrease over the simulation, but we are seeing those differences. So with the standard grip, those hands were right where that air was coming out of the vent. We do see that those reach a lower sensation than the other two positions. The other two positions, the right hand for the one are a little bit closer, left hand, one hand grip and low grip are a bit different. When we look at comfort, we see that they go from very uncomfortable and then reaching various levels of some higher comfort. So for both of these, again, the standard grip is reaching a higher comfort. And then the low grip is reaching a higher comfort than the one hand grip. And then we can look at local results as well for the lower arms. So again, here we have the left and right. With the standard grip, again, we see that that is, coming down as far as sensation goes. So coming from, very warm down actually into some slightly cool territory. So this is, dropping quite rapidly and then remaining around slightly cool. For the one hand grip and the low grip, we do see that come down, but it's much more gradual. If we look at the comfort results, we can see that with the standard grip, that does rise very quickly, and we actually come up all the way to a 4 of very comfortable. That is kind of a relief state from an uncomfortable situation. And so we rise up to a 4, and then you'll notice that it starts to come down. That very comfortable release state is not something that is sustainable in a long transient environment. So then we're going to come down, to a comfortable or just comfortable state. And then even at the end here, we see that that slightly cool starts feeling actually slightly uncomfortable. With the one hand grip and the low grip, we see more of a steady rise here. So we start out, in an uncomfortable state, and then as time goes on, we those two segments gradually start feeling more comfortable. And we see very similar results for the right lower arm. That state of relief happens a little bit after when it did for the left lower arm in the standard grip. Similar behavior though, we're coming up to a very uncomfortable and then that starts to taper off. One hand grip and low grip are just kind of this gradual feeling of more comfortable over the 15-minute transient. Sometimes it can also be nice to visualize the results on the geometry themselves. So what we're looking at here is we're looking at the local comfort results for each of the different body segments mapped onto the geometry. We can see the color range here at the bottom. So one thing to note here is that these are not temperatures. These are actually representing the local comfort values for those body segments. So -4 is this very, very deep blue, and then all the way up to red would be that very comfortable. So the deeper colors are feeling more uncomfortable, and then the warmer colors are feeling more comfortable. If we take a look at some of the results at 15 minutes, so this column that is most to the right, you can see some differences here. If we look at the chest, we can see some noticeable differences in that local comfort for those for the 3 different poses. We can also see a little bit that we saw in the graphs with the hands and the lower arms. You can see that depending on the different poses, we are seeing different comfort values, where the standard grip is more comfortable than the one hand and the low grip. So just a different way to view these results. And when we look at comfort, it's also helpful to look at sensation to know how the person is feeling. Is that coming from feeling too warm? Is that too cold? Just gives us more insight into the scenario. So again, here we're looking at local sensation values mapped onto the geometry, where blue is going to represent the cold ranges, white is neutral, and then when we move into the pinks and reds, those are the warm sensations. Again, if we look at the rightmost column and look at the hands and the lower arms, we definitely see differences when we look at the standard grip versus the one hand and the low grip. Also the chest, we're seeing some differences, and the face. So with the low grip, if we remember our velocity streamlines, they were coming up and sweeping the face in ways they didn't for the other grips. And we can definitely see that face. We see it on the cool spectrum, where with the other poses, it's still on the warm spectrum. This is just a look at the actual surface temperatures. So here we are actually looking at temperatures with the color bar here. So, once we've looked at all of the different boundary conditions and local results, we can see that we do see different surface temperatures. Different surface temperatures affect our skin temperatures, which then in turn affect our sensation and comfort results. And finally, just a still image here, again showing those surface temperatures. This is at the end of the simulation, and we can again see different surface temperatures with the different poses. So this does wrap up looking at this demonstration, and then a few other items that we wanted to introduce during this webinar. So for some additional post-processing for the human, there's a relatively new tool called the Thermal Comfort Analysis tool. This was built by Thermal Analytics Engineering, and it automates post-processing and interpretation of human thermal results. We've been using it internally a lot, and our engineers have been seeing a lot of value about this. So we just want to make our users aware of it so that they know of this tool that saves time and helps interpret results. So I'll just show briefly a little bit of the usage. So in order to use the tool, you specify the path to the TDF file, also the path to the TAITherm executable, and then the output file name. If you don't specify an output file name, it will just name the PowerPoint based on your TDF file. So all of the inputs are put up there, and then there's a few different buttons on the bottom. So create PowerPoint, that's going to create the PowerPoint file with all of the different results in your TDF directory. There's also some additional settings. By default, it's going to just show you overall sensation and comfort, and then the different body segments that are contributing to the overall values. If you open up settings, you can have it plot all of the different local results for the human, in addition to some additional human thermal outputs. And there's some information about the tool with the question mark. So when you click that Run PowerPoint button, what it's going to do is it's going to create a PowerPoint and Excel file in the TDF directory. And you can see an example of that on the right-hand side. So we've got this model report.powerpoint. The PowerPoint includes some different sections. It starts out with a summary of the inputs. This is very helpful because it will give you one spot to look at all of the different inputs to your human. This can be very helpful for figuring out if you have any errors in your inputs, because since it's shown to you all in one spot on the slides, it's easy to see if you made a mistake in an input and you could go back and correct it. After you've made sure that all of the inputs are expected, it then shows skin and core temperatures. These again are helpful to make sure that the scenario is as expected. So if you thought that you put, your person in a relatively neutral scenario, and then you see the hypothalamus temperature, changing by a lot, that would give you some indication that something, wrong is going on, that, they're not in this kind of neutral environment if their hypothalamus is changing drastically. Or with skin temperature, if that has an opposite trend than you were expecting, just good to kind of review those kind of as a next step. You'll also see all of the different environmental metrics. Again, that helps you to make sure that your scenario that you set up is what you wanted and as expected, and helps to understand what's going on with your human in the environment. And then finally, it will give you all of the Berkeley model analysis. So it's important that all of the other human outputs are reviewed first before you try to dig into sensation and comfort. And you can see an example of the plot here. So we have overall sensation, overall comfort, and then some different color codings based on comfort and discomfort. So again, we just find it, we've been finding it very useful for ourselves. So we think that our customers would also like to try it out. It's available for a free download at the Thermal Analytics support site. The image here is just showing what the article looks like. So if you go to our support site and you search thermal comfort analysis tool, you'll find this article, and there are downloads for both Windows and Linux versions. When we're talking about the different positions, also just wanted to introduce our human geometry database. So Thermal Analytics has been working on creating some different poses as well as different percentiles for humans. And so this table just shows where we are right now as far as the poses that we have and the percentiles for both male and female. So in conclusion, human positioning can affect overall sensation and comfort. The different positions affect how the airflow hits and then heats or cools different body segments. Thermal Analytics has a sophisticated human thermal extension that predicts sensation and comfort, state-of-the-art thermal solver, easy-to-use flow solver, and a growing human thermal database. Altogether, they provide a seamless tool set to explore all variables in HVAC design. And then just to leave with a few different questions. So now that we've explored the question of, does position affect sensation and comfort? And we've said, yes, it does. That does kind of create this first question here. So I only want to run one model. I don't want to run all of these different positions. Maybe I have certain constraints that just don't allow me to do that. What does TAI's experience in this study tell me about how I should set up one cabin run in terms of position and then all of the various human inputs? So for that, if you want to run only one model, we would say use a 50th percentile male or female in a standard driving position. This would hopefully capture, some sort of middle ground for, people as well as driving position. But what if I do want to study the sensitivity of a number of variables in an efficient way? How should I do that? We would recommend using TAITherm, a process automation platform that can automate setup and post-processing. You could sweep percentiles and position to determine best and worst case for a given HVAC architecture. And that concludes the presentation today. We'll now open it up if anyone has questions.
All right, thank you, Lauren. So yeah, let's get to some questions here. How long did the simulation take to run?
Yeah, good question. So these particular cases, the 15-minute transient on 24 distributed CPUs took around 7 hours to complete. That includes the volume meshing, the thermal runtime, as well as the flow runtime. And one thing to note is that, for this particular demonstration, we were not optimizing runtime. So it is possible that some additional time savings could be recognized if we investigated that.
All right, thank you. Are the flow results transient?
Mm. Yes, so RapidFlow is inherently transient, and coupling controls allow all types of steady or transient analysis with independent scales and time steps from the thermal analysis.
Okay, well, looks like that's it for questions. So that will complete today's webinar. We appreciate you all for attending. You will all receive a follow-up email containing links to download the presentation slides and watch the recorded webinar session. Again, thank you all. Thank you, Lauren, and everyone have a nice day.
Thank you. Have a good day. Bye-bye.